Thank you, and thanks for the invitation. So yeah, after, well, Gil talk was really good for me. Well, it was very good in general, but it was very good for me because she said everything that I need you to know. And also, yeah, we're in a very, very different setting, and what I'm going to do is very non-compact. I'm going to explain in a minute. But before I explain what IRSs are, because you all know what IRSs are, so I don't need to explain. But what are those? So we say that G is non-Archimedean if it's a closed subgroup of S infinity. S infinity is the permutation group of N. Okay, and we say G has no algebraicity if for all x1, xn, the stabilizer of x1, xn stabilizes no other points. So G is a closed subgroup of S infinity, so it has an action on N. I can look at the subgroup of G that stabilizes one given tuple. And so I said that G has no algebraicity if this is the only thing that is stabilized by this thing. In this case, G is not locally compact. This is going to be a big problem in a minute. But for now, let's see just a couple of examples. Well, S infinity is a non-Archimedean group with no algebraicity. If you look at the automorphism group of Q together with its ordering, if you see Q as N, well, this is a closed subgroup of S infinity, also has no algebraicity. And the last example is you take graph with vertex set N and put an edge between A and B with probability 1/2. What you get is the radograph. Well, almost surely you get something isomorphic to the radograph, and its automorphism group is a just subgroup of S infinity. So those are our friends, and those are the things that we're going to study the IRSs of. So if you remember from Yale's talk, the first thing she said, I think, was like, let G be locally compact. Here we work with non-locally compact groups. The first thing that we need to say is that IRSs are well defined. And for just this part, G is going to be a Polish group. I'm going to state two results that are true for general Polish groups, and then I'll go back to non-Archimedean ones. So G Polish, then sub G is not Hausdorff. Well, G Polish not locally compact. Not Hausdorff or Chaboty topology. So this is not the right setting to view it in, but it is standard Borel for the IRS Borel structure. So talking about IRSs makes sense. We have probabilities, so that's good.
Sorry,
The Chaboty topology. What?
I'm saying that the Borel structure still gives you a standard Borel space even though it's not Hausdorff?
Yes. So the other thing that we'll be interested in is so we have G that acts on X mu, and we want to know if we can produce an IRS using this. The way we classically do it by taking the stab application. And for the stab, that goes from X mu to sub. Oh yeah, I haven't said, but those are closed subgroup of G. Is mu measurable? Some analytic set intervene in here, and so like we don't get a Borel map, but it is mu measurable. So we're good to go. We have essentially the very basic stuff to work with.
So is it always true in the setting that almost every point is stabilized by closed subgroup?
Yes.
This is for Polish groups.
And yeah, this is basically the extent of what we know about Polish groups. We being Mathieu and I. But it's not, I mean, we work with non-Archimedian groups for a reason. And we do have the following theorem. It says, let G be non-Archimedian. Any IRS of G comes from a stabilizer. Mathieu thinks that someone in the room might have the answer to this question, so I'm going to ask it. Is it true for Polish groups? Because I have honestly no idea. I have no idea about that. The proof here really uses the fact that like we have the action on N that does a lot of the heavy lifting. Yeah, so we'd be curious about that. Okay.
So if it's true for like homomorphism, like the sphere or something?
I don't know. I know for an Archimedean, and that's it. And there's something else that is known about IRSs of S infinity. This is a result of a Kerman, Fourier, and Patel. 2012. That says if G is a closed subgroup of S infinity with no algebraicity, then there is a S infinity IRS supported on the S infinity orbit of G. If you try to do it, well, so I gave you 3 examples. For S infinity, it shouldn't be too hard. For odd Q, you can do that somewhat easily, and the definition I gave you of the radograph gives you explicitly a way to do this, right? You have a random graph, you take the automorphism group, this is going to be an IRS S infinity. What I've hidden under the rug is that there are some very nasty non-Archimedean groups, and like this is very not easy to do in general. Very quickly, you try to do it for very explicit subgroups, and this result is not easy at all. So yes, that's what was known, and with Mathieu, we prove something, well, somewhat in the other way around, which is to say, let G be a definity group. I'm going to define definity in just a sec. Then, for all new IRS of G, there is H closed subgroup of G such that mu of the orbit of conjugacy class of H is 1. Let me define the definity group, and then I'll comment a bit on this result. Yes. Here. So a definition G is definity if for all tuple X and O orbit of Gx and N minus X, the only ergodic invariant probability measures on 0, 1 to the O are product measures. This name, definity, refers to the classical definity theorem that says that if a family of random variables are extensible, then they're IAD. This is a refinement of this notion with actions of groups.
It's a finite number. It's like saying like an n tuple, a k tuple.
Yeah, it's a k tuple, exactly. Yes.
Definitely assume the ID condition on some other variable.
Ergodic invariant. Yeah, so classical definity tells you at infinity is definity. And with Tudor-Tsunkov in a paper from last year, there are a lot of non-Archimedean definity groups.
Can you give another example of one of these many?
Yes, OT R. Yes, and OT Q is also. But I don't want to give a general description because this would use terms from model theory, and I don't want to do that here. And basically, definity groups are the right setting to, I mean, it's a lot easier to work with definity groups because you have some independence when you look at things that are far away, and that's really useful.
You have a logically compact definity?
Yes. The financially supported symmetries of N, which is the actual original definitive proof isn't this.
But it's for a specific action. I mean, if you're in your definition, it depends on the embedding of G in a specific, right?
Yes.
Okay.
Yeah, so that's about the definition and the hypothesis of this theorem. About the conclusion. This is remarkable for two reasons. Well, the first one is that actions of S infinity can be properly ergodic, meaning not like that, not supported on an orbit. And also, our result is not always true for locally compact groups. So yeah, I don't know. Non-Archimedian groups are their own things, I guess. Something else I wanted to remark on here is that the proof uses very little model theory. And I want to insist on that because we spent so long trying to reduce the amount of model theory in there.
Why not always following?
There are locally compact groups that have IRSs that are not supported on orbit. Definitely? No. Yes. I mean, otherwise we would have a problem.
So about the second bullet point, is the fact that you use the model theory remarkable, or is it remarkable that you can use very little bit?
The second part. And also I said two things were remarkable. Those are those two. This is not remarkable.
So okay, let me restate my question. It still stands. So how unexpected it is so that we have to use model theory?
No, it's very logical.
Mm-hmm.
I mean, non-Archimedian groups come from model theory in a way. So it's really the natural setting. What's not natural is that we had to study invariant random models. Wanted to call them invariant random structures, but not a good acronym. And so we have to study invariant random models, and we ended up proving things on those that were not expected. But in the end, we only use first order logic, which everybody knows. So that's was there? No. Okay. Oh yeah. Also, yes. Also, those two theorems look very similar, because this says, oh, all IRSs they are supported in an orbit, and this says if my group has no algebraicity, then but here I said nothing about no algebraicity. So we get slightly more things as IRSs than just that, but not a lot. Basically, what we have is that an IRS can have algebraicity, but so take H support of IRS, then if Hx stabilizes Z, who is Z not in X, then the whole group stabilizes Z. So with IRSs, we're allowed to have some algebraicity, but it's only by having fixed point. You will never get more than just your fixed point, and then the rest of it is basically this way. Okay.
Are there groups without an IRS supported on the conjugacy, subgroups of S&P?
Yes. The ones with a lot of algebraicity.
Not all of them.
Well, this is the condition. Like if you have algebraicity that only comes from fixed point, then you have an IRS, and if not, you don't.
Any discrete group can be made of a subgroup of S infinities, like F2
And so it's clear that with one piece of
then yeah, you can have, I mean F2 has many.
You will have algebraicity. Is
conjugacy, I mean, the conjugacy class depends on the way you embed it. Take the regular app.
That you are calculating, like, is there a way to intuitively think of them as like not cofinite, but like books with cofinite normalizer, like with multi-complex books? I mean, I know there is no natural measure, but you can tell that.
I think the analogy is more lattices, but I also think the analogy is not really good. So the answer is basically I don't know. And just to finish, well, there is this question is so we have IRSs of S infinity. Do we have IRSs of subgroups of S infinity? So the first thing is that if H is an IRS of S infinity, then G intersect H is a non-trivial IRS of G. Unfortunately, not all IRSs are produced this way. Oh, IRSs.
Yeah, I'm assuming that G intersects this conjugacy class of H.
Yeah, no.
It will always be non-trivial.
Yeah, that's kind of weird. And I've been authorized to call that a conjecture. If H is a closed subgroup of G, H has no algebraicity, there is an IRS of G supported. Yeah, this is a conjecture or a theorem. I have a proof, but we haven't yet checked it properly. So yeah, that's about what I wanted to say about IRSs. Thank you for listening.
Thank you very much for this talk. Any questions or comments?
That's good. So it's for, I don't know what level of generality, but say for poetry, but if the answer for a smaller class, I'm happy with that. But for Polish groups, so is there a natural compatible G invariant Polish topology on sub G?
No.
Wait, precisely prove no.
Okay, not that we know.
So it's like if H is an IRS, then it's non-trivial in every subgroup. So it's a lemma, it's a theorem. It's like how long is it?
If you, from the model theory perspective, this is actually very easy. From the group perspective, you have to do an argument, but it's not hard.
So IRSs on sub G in locally complex groups have some nice regularity properties. I mean, the regular measures is there anything equivalent here? I don't know, at least positive on open set or something.
I don't like they're really well behaved, but I wouldn't have a precise characterization. The theorem of a common Fourier puzzle gives us a lot of understanding of like how those behave. So yeah.
Once again, since they're just considering sub G as a standard Borel space, there's no topology.
There is a topology.
No, topology just from house. So.
Yeah.
Oh, you're asking for that topology. I was listening about that before. Okay. That's apology already not nice.
The thing is that we have the space of models that like is just above the space of subgroups, and this space is really nice, and we can use the niceness here to work on there.
Is there a better topology than your topology?
Not that I know of.
Wait, what do you mean by that? What do you mean?
I mean, the answer is yes, that from abstract nonsense, that from Becker calculus, right? That there is a Polish topology
Yeah.
that is G invariant. So
The thing is that it's not natural. I mean,
yeah, so exactly.
the
So,
pretty much whole way of describing this topology with only the group itself.
so in the proof that it's standard Borel using the Borel structure, you presumably.
You need to the subset.
Yeah.
Okay, but at least.
I mean, like, yes, but for any concrete purpose, no. At least for us.
You could fix like a left invariant metric on the group, and that would give you an actual topology, right? Like a slice thing. That's not horrible.
But there are many of them.
Yeah, it looks like that. My favorite one.